Set the controls for the heart of the sun. It's a dramatic statement familiar from movies and music, but now a new mission really is ready to plunge into the atmosphere of a star. Not just any star, our star, the Sun. 60 years in the making, the Parker Solar Probe is primed to reveal the true nature of the heart of our solar system and the source of the solar winds. Weighing just 685 kilograms, the solar probe was launched aboard a ULA Delta IV heavy rocket. Its thrust of 9,700 kilonewtons may seem like overkill, but the Parker probe has to travel faster than anything before. As a matter of fact, it will be the fastest man-made object ever launched.
Parker Solar Probe really is a historic mission. It was first dreamed of in 1958, and it's remained the highest priority mission throughout that period. The reason it hasn't flown is just because it's taken a while for technology to catch up with the dreams that we had for this amazing mission.
Destined for the Sun, our star, this probe is the realization of a dream that has been evolving over decades through the talents of hundreds of dedicated people.
After working on this for 10 years, it is really a pleasure to see it kind of actually coming to fruition. To be one small part of this huge engineering team that is making science dreams come true is just amazing. I can't wait to rewrite textbooks and change the way we look at the sun forever. I'm really excited to pass this off to the mission operations team and see all the science data that comes down and just get to enjoy all that Solar Probe brings us.
This is a 60-year journey that people have gone on to make Parker Solar Probe a reality. And to be there at the finish line, that is definitely the coolest thing about my job.
Several questions arise. How did this project get started? Who was behind it? And why is it called the Parker Solar Probe? It's because of this man.
The Parker Solar Probe is the first mission ever to be named after a living person, our own University of Chicago astrophysicist Eugene Parker.
Born 1927 in Houghton, Michigan, Gene Parker gained his PhD from Caltech in 1951. By 1958, he had developed his theory on the supersonic solar winds and predicted the shape of the solar magnetic field in the outer solar system, which now bears his name, the Parker Spiral.
So Gene Parker had graduated in physics and had a hard time actually getting a job. So he was first doing some researching at University of Utah when he was then invited to come to Chicago. He was not sure he was going to make it in the field. When he wrote his paper, it didn't help that the referees were not in agreement with him and didn't really want to publish his work. So he had lots of challenges early on, but he was right. And this is one of the things that first helped him, be the person that we all recognize as this amazing role model to all physicists, but also the power of science being right or wrong due to experiments. So what vindicated him was not just having Chandrasekhar, for example, helped him publish his article, but what really made him who he is in the history of science is the fact that the measurements showed him right.
I think that's an interesting thing.
This one piece will make 52 layers.
Watch on mobile devices or the big screen. All for free. No subscription required.
Eugene Parker has received many accolades over his career, including the National Medal of Science for Physical Science and the title of S. Chandrasekhar Distinguished Service Professor Emeritus at the University of Chicago.
So in 1958, Gene Parker realized that the sun has a magnetic field and it will have a structure around the solar system that will be populated by what we call plasma. So these are hot particles that are flying from the sun all the way to the edge of the solar system. This is what he called the solar wind. So the solar wind is a structure generated by the sun, which basically envelops the whole of our solar system all the way to the edge. And it has been studied all the way to the edge of the solar system with, for example, the Voyager probes, which are now crossing into what's outside of the solar system, which is the furthest that man has ever been, or any man-made machines have ever reached across the solar system.
I laugh about this because I remember how upset some people were. They insisted I made a mathematical error, and I would reply, well, here you are. Here's 5 lines of algebra. You say I made a mistake. Show me. And it's amazing the number of people that just couldn't let go of the old ideas. They've been working on the spacecraft for several years, and one day the phone rang, and it was a guy that I know said, we're talking about putting your name on the Solar Probe Plus, it was called. And did I object? And I sort of said, no, I feel rather flattered. So he said, okay, that's what we'll do.
While the success of this mission bearing his name will not be known for many years to come, all the effort is sure to be worthwhile. The advances in engineering required to make this mission successful have been far-reaching and at times ingenious. That's because the speeds required to reach the sun are mind-boggling in themselves.
The solar probe will be reaching the closest ever to the sun and moving the fastest and reaching the hottest regions of the solar system. It's so fast that it could go from Chicago to Beijing in less than 1 minute.
There are many enabling technologies. The solar arrays were very important. The autonomy was very important. One of the ones that was obviously also critical was the heat shield, and developing the technology to actually protect the probe at the sun.
The Parker Solar Probe is a technological marvel. The thermal protection system, the heat shield, will be glowing cherry red. The front surface of that will be 2,500 degrees Fahrenheit, while the spacecraft remains 85 degrees, roughly a warm day in Florida. The material sciences just didn't exist in the 60s and 70s. And so the carbon, which came out of, frankly, the military, looking for lightweight, stiff, strong structures, were the precursors to your tennis rackets and golf clubs, which are now the precursor to the carbon-carbon technologies that we have on Parker Solar Probe.
Temperatures so close to a star can reach a phenomenal range. Serious sun screening is required.
And a sandwich panel is a lot like a honeycomb panel you find in a traditional spacecraft or on airplanes. You have 2 outer face sheets, and then you have a core. In this case, the 2 outer face sheets are carbon-carbon composite, which is a lot like the graphite epoxy you might find in your golf clubs. It's just been superheated. And then the inside is a carbon foam. So the Parker Solar Probe heat shield has a white coating that's on the sun-facing surface of this giant frisbee that's protecting the rest of the spacecraft. And that white coating was specially designed here at the lab in collaboration with RED and the Space Department, as well as the Whiting School at Johns Hopkins proper, to actually work at the sun. This was specifically designed for Solar Probe. And the concept is basically you'd rather be in a white car on a hot day than a black car on a hot day. It's just that it just knocks down the heat that much more. And so it's helping us stay cool at the sun. That titanium truss was also specially designed for Solar Probe. It's actually a really neat piece. It's a welded titanium truss that's about 4 feet tall, but it only weighs about 50 pounds. And the key there is we're trying to minimize the conduction between the heat shield and the spacecraft. So you want to have as little stuff there as possible.
The hottest environments in the solar system will be probed by this mission, and its instruments that will be measuring all the different properties of the solar corona are protected by a shield, a state-of-the-art shield developed by NASA, which would make Captain America very envious. This shield keeps the instruments behind from being cooked every time the probe gets really close to the sun. So the shield made of reinforced carbon is really something that is very recent technology, and only now we can actually get that close to the sun and really verify some of the predictions that Gene Parker has made over his whole lifetime of trying to understand the solar wind.
Earlier iterations of this spacecraft design were predicated on a nuclear power supply. That idea was dropped in favor of solar panels, which brought their own design difficulties so close to the sun.
Parker Solar Probe needs electrical energy to operate. Like any other satellite, or most other satellites, the spacecraft has solar arrays. But unlike other satellites, we have to generate electricity very close to the sun. For every watt of electrical energy we generate, we have to dissipate 13 watts of thermal energy. To do that, we need a cooling system, and we have a cooling system that's much like you'd find in your car. There are 2 water pumps in the system that pump water through the solar arrays and up into radiators. Those radiators radiate the energy to deep space, which is very cold, as opposed to like your car where it would be radiated to air.
When we're at closest approach, the front surface of the heat shield will be at about 2,500 degrees Fahrenheit. The back surface of the heat shield will be about 600 degrees Fahrenheit. But then the spacecraft bus is basically sitting at 85 degrees Fahrenheit. So the shield is actually really keeping everything very cool, and that's most of the stuff is on the bus.
If you look at the science data, there's a big gap, and that gap is where Solar Probe is going. We're going to fill that gap of scientific knowledge. So it's true exploration. I mean, in that, and we're not following somebody. We're the first spacecraft, first people to go there. So what will be interesting is not the answers to the science questions. What will be interesting is the new questions that Solar Probe forces us to ask. Because one thing we're pretty sure of is that probably have it somewhat wrong. And Solar Probe will teach us what's right. And that'll generate many, many more questions and many more missions to come.
NASA's Parker Solar Probe will soon fly closer to the Sun than any spacecraft before it, some 4 million miles from the visible surface. But getting that close to the Sun requires some fancy orbital mechanics and a dash of brute force. Why is it so hard to get to the Sun?
Another reason Parker Solar Probe wasn't launched in the last 60 years is that getting so close to the Sun is hard. It takes a huge amount of energy to get to where we want to go. When a satellite lifts off the Earth, it carries the Earth's velocity around the solar system. So the Earth is moving at about 30 kilometers per second around the solar system.
Of all the space missions I've worked on, Parker Solar Probe is the most challenging and complex mission to design and to fly. The launch energy required to reach the Sun is 55 times of required to get to the Mars and 2 times to Pluto.
Traveling so close to a star can also affect communications with Earth. In such a dangerous environment, engineers had to design software with serious smarts.
So Parker Solar Probe uses a sophisticated rule-based autonomy system to protect itself. For long periods of time, the spacecraft can't communicate to the Earth, and it needs to take care of itself. So the engineers during the development phase spent a lot of time thinking about what faults could affect Parker Solar Probe and came up with solutions for those faults. Those solutions are encoded in this rule-based autonomy system so that even if there's a fault on orbit, which of course we hope there isn't, the system can take care of itself. One of the most common questions I get are, what happens if the spacecraft gets hit by a solar flare or gets hit by a coronal mass ejection? Will it be destroyed? That's a very common question. And what I tell people is the science community will be elated if we were to get hit by a solar flare or a coronal mass ejection. They're very dramatic events when you look at them in a telescope or during an eclipse. But in the reality, they're very ethereal. The density of the particles isn't so high from the point where it could actually cause damage to the spacecraft. But the instruments aboard the spacecraft, the electromagnetic field instruments, the high energy particle instruments, the plasma instruments, and the visible white light sensors will see this event. And how dramatic would that be to see a solar flare coming at you and to fly right through it?
The sensor suite on board the Parker Solar Probe is indeed impressive. Each was designed to withstand the harsh radiation and temperatures to measure the particles, electric and magnetic fields of the solar wind. There is also an imaging instrument on the spacecraft called WISPER.
The WISPER instrument is the only imaging instrument on the Parker Solar Probe, and it is looking in the direction that the spacecraft is traveling. And what it sees is light scattered by the dust that's in orbit about the sun. But then, once we remove that, what we see is the light scattered by the electrons in the corona, in the solar wind. These measurements that we're making from the WISPER instrument have been made before by other instruments from 1AU, from the distance of the Earth, about 100 million miles from the sun. By getting closer, we're increasing then the ability to see what's really close to the sun. The fact that you're close means that you don't have all this material that's in between you and the object that you're really interested in. And that contributes to background noise. And so you're looking at something that's much more pristine. You're looking at just that object all by itself.
We have 3 sensors that measure magnetic fields that are mounted on a boom behind the spacecraft in the shadow shield. And then we have 5 sensors that measure plasma voltage. These are electric field sensors. They extend into full sunlight and they get very hot. There are 2 ways to measure electric fields in space. One is using a technique that's called a double probe. Then there's another technique which is measuring plasma waves or radio waves. And Fields for the first time brings these 2 techniques together. I think the very first data that we get will be revolutionary. At first blush, it'll just be a bunch of numbers as a function of time. But the science team, will take those numbers and make visualizations in the form of spectrograms, and eventually those data will be related to models, and so we'll be able to compare directly the 3D visual models of the coronal magnetic field. 2 of the key measurements to understanding coronal heating are the measurement of the magnetic field and the electric field, and together they give us what's called the Poynting flux, which is the energy flux of the corona. And to make those measurements, we have to actually go into that plasma and put sensors in the plasma to measure magnetic fields and electric fields directly, and that's what Fields will do. These measurements have never been made in the environment close to the sun. We've made measurements similar to this in the Earth's magnetosphere, Earth's ionosphere, but putting a package like this into the solar corona it's just never been done. The closest anyone's ever been to the sun, and based on what we've seen so far from spacecraft not quite as close, it's going to be striking and I think revolutionary.
The other science packages aboard Parker include SWEEP and ISIS, designed to study the particles emitted in the solar wind.
ISIS, the Integrated Science Investigation of the Sun, is an experiment which looks at energetic particles over a broad range of energies, from tens of thousands of electron volts up to about 100 million electron volts. The ISIS instrument is based on solid-state detectors. Those are detectors that when a particle passes through them, energy is deposited, and you can measure that energy, and you can measure that the particle has actually passed through. So there's the solar wind, which is this continuous flow of lower energy particles. And then there are much more sporadic and episodic events like solar flares that spew out great numbers of these much more energetic particles. In our higher energy instrument, we have a whole set of layers of these detectors. And when a particle passes through those layers, it leaves energy in each and every one of those detectors. Those detectors are also segmented in pieces like a pie. And so when a particle comes through from a particular direction, you can tell both the direction the particle came through at, and you can tell the energy and species of that particle.
The SWEEP investigation consists of 3 separate instruments and a central electronics box. Most of the instruments within SWEEP sit on either side of the spacecraft, stare out over the entire sky, and make maps of all the different particles and what energies they're moving at, what types of particles they are. The purpose of SWEEP is to measure the bulk of the solar wind and the solar atmosphere. One of the biggest questions we want to resolve with Solar Probe is how the corona and the solar wind are heated. In order to do that, we need to see if there are waves that are coming from the sun and depositing energy within the solar atmosphere and in the solar wind. So we have a series of sensors across the spacecraft that will collect individual particles, electrons, fully ionized hydrogen and helium, which we call protons and alphas, and other minor ions, and make maps of the number of particles as a function of their speed and energy and type. We take those maps on the ground and we can interpret them to figure out the temperature, the density, the pressure of the solar wind and the solar atmosphere.
Learning the secrets of our star, the Sun, will help us understand the nature of the solar system and its all-embracing influence on our world. But the Parker Solar Probe is not the only mission destined for that star. The European Space Agency is also in the game. In collaboration with NASA, the Solar Orbiter is set to launch very soon and will be joining Parker in its quest for knowledge. The orbiter will fly an elliptical orbit within the orbit of Venus, but on a much greater inclination off the ecliptic, giving it access to the poles of the Sun. Unlike the Parker probe, the orbiter's main observation instruments will peer through the solar shield at a safe distance, then reconfigure when making a closer approach. Together, they will reveal the secrets of our closest star, the Sun. The cryosphere is the ice mass of our planet, the ice sheets, permafrost, and water ice of the poles. A moderator of ocean and atmospheric temperatures, a sun reflector, the cryosphere is an integral part of this planet's cooling system. Climate change is shrinking the ice caps, and it's a runaway effect. Our world is warming, the oceans are rising, and we need to do something about it. Of all the fresh water on Earth, 99% is stored in ice sheets, the large frozen masses that form over land. As climate changes, Melting ice sheets can contribute to rising sea levels, which can place vulnerable cities around the world in jeopardy. From the South Pole to Greenland, from Alaska's glaciers to Svalbard, NASA's Operation Icebridge covered the icy regions of our planet in 2017, with a record 7 separate field campaigns. The mission of Icebridge, NASA's longest-running airborne science program monitoring polar ice, is to collect data on changing ice sheets, glaciers, and sea ice, and maintain continuity of measurements between IceSat satellite missions. World-renowned leading climate scientist and astronaut Dr. Piers Sellers was director of the Earth Science Division at NASA Goddard. Having seen Earth from space on 3 shuttle flights and 6 EVAs, Dr. Sellers was deeply concerned for the future of our climate.
Now, Icebridge is probably one of the most important field campaigns we have running right now. The world is warming, and it's warming faster in the north, around the Arctic, than anywhere else by a factor of 2.5. It's 2.5 times increase in warming here compared to the global average. So this is where it's all happening. And as a consequence, the ice is melting fast. It's melting on the Arctic Ocean, and the ice mass on top of Greenland is melting and falling into the Atlantic. So we're mapping that using aircraft and satellites where we can. And of course, we've got people on the ground checking against these data as well. So this is ground zero for global warming. We're doing a lot of work here. We put a lot of effort into it. And I think it's paying off in terms of improved understanding.
Operation Icebridge began in 2009 and continues to fly aircraft through the region with advanced sensing equipment and coordinated land traverses by scientists to ensure accuracy of satellite data. Now, in conjunction with the European Space Agency, they coordinate and share data with additional satellite assets which fly identical science instruments. Just why are the ice caps melting? Because of the so-called greenhouse gases, carbon dioxide, methane, nitrous oxide, and fluorinated gases in the atmosphere. Together, they heat up the atmosphere by trapping energy. While CO2 has always been part of the atmospheric makeup, it has changed since the Industrial Revolution.
In the pre-industrial age, the CO2 response to temperature was that the temperature would go up and CO2 would go up. Or if the temperature went down, CO2 would go down. And the reason for that is when the temperature went up, the whole biosphere revved up and emitted CO2, and we had more CO2 in the atmosphere. So we understand that process. The problem for the science community is in the post-industrial age, the CO2 rise is preceding the temperature rise. So 2 different things happened. One, pre-industrial, where temperature was driving the CO2. Post-industrial, where the CO2 is driving temperature, which means a completely different physical, biological process is going on. And we don't understand what the consequence of that change is. It is a fundamental change to how the Earth works and how the Earth's radiation balance works. And so, since we don't understand it, we're very concerned because we don't see any restraining force on continued increase in temperature due to continued increase in CO2. And that's a problem.
Warmth tipped the scales again with the hottest October on record, but also the 4th hottest year to date for the globe, according to a fresh analysis by scientists at NOAA's National Center for Environmental Information. Generating long-term data sets is extremely important when studying climate. So, to maintain continuity, a new generation of Earth observation satellites are coming online. ESA have deployed Aeolus, METOP-3, Sentinel-C, and NASA have launched IceSat-2, the JSSC, and the follow-on GRACE missions. All of these satellites have one instrument in common that measures altitude.
A radar altimeter is a beautiful instrument because it measures almost everything we need on the planet. It measures the height of the sea, the height of the ice caps, but also we can use it to measure the heights of lakes and rivers, even derive river discharge.
METOP-C, the third in the METOP program, carries no fewer than 13 observational instruments. Some are identical to NOAA's suite of satellites.
We have 10 instruments on board METOP. It was a very large platform. And these instruments are also provided by different organizations. We have a set of instruments provided by NOAA NASA. We have instruments provided by CNES. We have instruments which are procured by ESA, and some other instruments which are procured by EUMETSAT directly.
So METOP-C is the last satellite of a cooperation program that we have with the NOAA in the United States as part of what we call the initial joint polar system. So in 1998, EUMETSAT and NOAA signed this cooperation agreement where three European satellites, or three METOP satellites, were corresponding to three US satellites. And for these satellites, we share instruments so that the users get information from both satellites, the same types of information. So we try to create synergies between US and Europe, more benefits to our user.
We didn't expect we'd be able to measure sea level to just a few millimeters every 10 days. And having such accurate measurements for 25 years has let us monitor sea level rise and even perhaps detect an acceleration in the sea level record. And that was something that wasn't envisioned 25 years ago. But as the technology has gotten more and more accurate, we've been able to make more and more accurate measurements of sea level. And so we can be even more confident in our results. Combined with, we have other observing systems other than altimetry. We have a gravity mission called GRACE, where every month we weigh the ocean. And we have robots that float throughout the sea, about 3,000 to 4,000, that take the temperature of the ocean every few days. So when we add up the results we get from the gravity mission where we weigh and where the Argo floats where we take the temperature, we get almost exactly the same answer that we get from the radar altimeters, to within a few millimeters. So we're very confident in our results that we're seeing 25 years of sea level rise of about 3 millimeters per year, which doesn't sound like a lot, but as we see it starting to increase year after year, we know that acceleration will be very devastating for coastal communities all over the world.
Aeolus, ESA's newest Earth Explorer satellite, with which the agency will measure wind profiles from space with laser technology.
At the moment, we have a very poor understanding of how the wind is around the globe, and we need more knowledge about that. But that's the information you need to start. You need to have a picture of how is the weather now to be able to predict how the weather is in the future.
Aeolus is a relatively short mission to demonstrate the potential of the Doppler wind LiDAR in space. And once we can demonstrate that actually it's made a decent impact on the numerical weather prediction forecast, then hopefully we can have an operational follow-on mission, or maybe several satellites in tandem rather than just one satellite. It's not just wind information, actually. You need to also know temperature information, pressure, and humidity information. But the winds are a key component of that information that you need to know right now to work out the weather in the future.
Sentinel-3A was launched in 2016 and 3B in 2018. Both satellites primarily focus on our oceans. They measure the temperature, color, and height of the sea surface, as well as sea ice thickness. These measurements are needed to study changes in sea level, marine pollution, and biological productivity. Sentinel-3A has already yielded interesting results.
The Sentinel-3 mission is actually quite a versatile mission in the sense that it serves a large variety of different Copernicus services. So we're not just working with the Marine Environment Service, we're also working with the land, with the atmosphere, and with the climate service. There's a large variety of data that we can actually supply. The Marine Service is probably the most developed for the moment. It's already using data over the ocean, in particular the ocean color data, which tells us something about the marine ecosystem, about the health of the sea, and can basically also predict something like harmful algal blooms. Snow cover gives us an idea about the snow water extent. So basically that gives us an idea of when this melts, for example, where we go in terms of flood forecasting, runoff models, so for hydrological applications, but also for weather forecasting, for example.
Sentinel-3 mission is supposed to last until 2040 at least. So A and now B will be in space soon. The C and D model, which are replica of this one, are under manufacturing now and will be completed by the end of the decade. And they are expected to be launched in the 2023-24 timeframe to cover basically the Sentinel-3 mission until 2030.
That's why we want to have continuous measurements. So we have planned with the next series of JASON missions, JASON CS or Sentinel-6, that we'll have at least 10 more years of measurements because we need to keep monitoring the sea level as it accelerates.
With this long-range forecasting, the acceleration of global warming can be monitored and better predictive models developed.
Yes, that's why by having all three measurements, that helps us understand the cause, that we can see from GRACE a measure of which continents the water is coming from, that Greenland and Antarctica are melting, and some glaciers are also melting. And we can also see as the temperature of the globe increases, we can watch the water in the ocean actually expand for more and more heat.
Scientists on the ground continue to innovate ways to improve satellite data accuracy. Surfing for science may seem far-fetched, yet that is exactly how Dr. Bob Bruin of the Plymouth Marine Laboratory is pioneering a new technique in satellite oceanography. By equipping his surfboard with a device called a SmartFin, Bob can measure sea surface temperature and motion of coastal waters with his smartphone. Later, Bob can use the SmartFin data he has gathered to better interpret Sentinel-3 satellite data. The Sentinels are part of the Copernicus program. Using the three instruments on board, the satellites gather information on ocean color, water quality, changes in sea level, and, most important for Bob's research, sea surface temperature.
With over 40 years of thermal radiometry we have now from our satellite platforms, we can begin to get a really good understanding of how temperature is changing in the nearshore environment. And temperature is a critical component of our oceans. It controls the biology through changes in growth rates and reproduction. It controls the physical environment together with salinity. It controls the density of the ocean, how coastal currents move, and it's also a fundamental component of marine chemistry. The reaction rates of many chemicals are temperature dependent. The gases that move from the atmosphere to the ocean are temperature dependent.
In situ data gathered by scientists like Bob is extremely important as it complements and helps to verify data provided by the Sentinel satellites. For example, the temperature of coastal waters is difficult to measure from space, though they have very high levels of marine biodiversity. So scientists find new and ingenious ways of increasing the number of in situ measurements in these waters. With the SmartFin, for instance, surfers and other water sport enthusiasts can gather data while enjoying their hobby. Meanwhile, NASA has dispatched 2 new satellite missions to observe the most critically changing regions, the poles. NASA and the German Research Center for Geosciences, GFZ, has launched GRACE-FO, continuing the revolutionary gravitary measurements of its predecessor, GRACE. ICESat-2, with an advanced laser altimeter system, is continuing the work of its predecessor. This new technology will help study ice sheets, but also sea ice, glaciers, permafrost and snow cover. Collectively known as the cryosphere, These frozen zones help sustain stable conditions for life on Earth.
ICESat-2 is NASA's latest technology to measure the elevation or the height of ice sheets, and by repeating those measurements through time, we can measure how ice sheets are changing. It'll also allow us to measure the height of sea ice, which is a way to understand the thickness of that sea ice. And so it's really a huge advance forward in both our precision of elevation change measurements as well as coverage. Each of those 6 beams gives us much more data than we've ever had before. ICESat-2 was designed and built here at NASA's Goddard Space Flight Center, and it does take advantage of many of the latest advances in that technology. It's really an excellent tool for studying changes in ice sheets and in sea ice. For sea ice, it's really critical. It plays a first-order effect in weather patterns around the world. Sea ice in the Arctic Ocean regulates the exchange of heat and water vapor between the ocean and the atmosphere. And as sea ice gets thinner or thicker, it either allows more or less of that heat exchange to happen. For ice sheets, as that ice is lost back to the ocean, it directly goes into sea level rise, which of course impacts folks worldwide.
So NASA scientists crossed the Antarctic, taking altitude and radar depth measurements to help calibrate ICESat-2's instruments.
One of the other experiments we were doing is leaving out what we call corner cube reflectors to get an assessment of the pointing of ICESat-2. When we make an elevation measurement, how are we sure it's in the right place? So in this picture, you can see a bamboo pole with a little white cap on the end of it. And embedded in that cap, a little piece of glass about as big as your pinky nail, and calibrated to return green laser light from the satellite.
With the requisite observation tools in place, the next step is to interpret the data.
Ice sheets are actually really dynamic, and they flow under their own weight from the center of the ice sheet out to the perimeter of the continent. In the really cold regions and way high up on our ice sheets, we get a lot of snow accumulation, and over time, that accumulation can build up. If it stays cold enough and that snow persists, and then you get another year of snow and another year of snow, you can imagine the weight of the snow on top of itself forces some of the lower layers to compact. We call that the firn densification, the top layer of the ice sheet. When we talk about the health of our ice sheets, we talk about the mass balance of the ice sheet. Basically, that means coming in is in balance with all the terms of water or ice going out.
The health of the ice sheets depends on a balance of these terms of input and output, but the interaction of the atmosphere, ocean currents, and temperatures can force the ice sheets out of this equilibrium.
At a big scale, the winds in Antarctica are kind of spinning in a big clockwise direction around the continent. But you can imagine a big dome of ice has very little obstruction, like trees or mountains kind of steering the winds. Consequently, winds that sort of are gravity-driven and come down the continent can build up speed really quickly, and again, uninterrupted by any sort of disturbance. And we call those katabatic winds. And they have a major influence on what happens at the edge of the continent. Around Antarctica, there's a massive current that we call the Antarctic Circumpolar Current, and it flows clockwise around the continent. Close to the continent, we also have the Antarctic Coastal Current, stays really close to the coastline and flows counterclockwise around the continent. In addition to these continent scale currents, we also have regional scale currents, such as gyres. Gyres are these parts of the oceans that are sort of isolated because of topography or ocean bottom topography. They're usually closed currents that often circulate. The gyres have a big role in sea ice formation and also in the currents that actually flow underneath our ice shelves. You can imagine that around the edge of the continent, near those ice shelves, warm water from the ocean can intrude into that cavity and contribute to basal melting, the melting from warm ocean waters of the bottoms of our ice shelves. Calving in Antarctica is a little bit sporadic and it's hard to actually model, but some of the contributing factors associated with calving include those strong katabatic winds pushing on the edge of the ice sheet, pushing on the edge of the ice shelf, and calving large icebergs. So we're measuring surface elevation, and we can take that vertical measurement, kind of integrate it over the whole ice sheet and get a volume change. And then the real science of ICESat 2 is taking that volume change and turning it into a mass change. And from that, we can determine how much ice is actually turning into water in our oceans and raising sea levels. So the Greenland ice sheet is thinning, and it's thinning variably, but mostly along the coastlines. It's thinning beyond our expectations. And all of that thinning is taking place upstream of where the ice sheet is grounded. Therefore, that is going right into the ocean and contributing to mean sea level rise.
Since we launched ERS-1 in 1992, we have been working on the radar altimeter time series, and we have derived a 25-year-long time series of sea level rise. Sea level rise is a major indicator of climate change because it integrates, for instance, the melt of Greenland and Antarctica. We have analyzed this series, and we have analyzed the error, which is under control, and so the scientists are convinced that now we have clearly on average 8 centimeters of sea level rise, but we also have regional variation. For instance, in the tropics, it's 3 times that value. And what we have also analyzed with the recent data is that in the last 5 years, sea level has been accelerating. And so it's not 3 millimeters per year or 3.2 millimeters per year. It's more like 5 millimeters per year. We have provided this data to people doing projections, to scientists, climate change scientists doing projections, and they have modeled the sea level in 2100, which is expected to be 2 meters higher than today.
This animation shows how different the globe will look by then, and prompts us to consider where the food and fresh water will come from.